Cool. Can everybody see the slideshow then? Awesome. All right. Well, welcome and good morning, afternoon, evening. Today, we're going to talk a little bit about best practices in management, integration, and visualization of resource data. So I am Sarah Arpin. I work for the Kentucky Geological Survey. There, I manage the Kentucky Groundwater Database Repository. And then I also do some volunteer work with the Kentucky Geological Survey. And so that's a nonprofit organization really based around managing cave data. And then Pat?
And I'm Pat Kambesis, and I'm the faculty at Western Kentucky University, and I teach various different, geo-related courses, and I am also part of the same organization that Sarah just said, the KSS, among many other things. And so we're kind of excited. We've been working on this for months, right, Sarah?
It's amazing.
About best management practices in data, since we're all so steeped in data these days. And
So,
we're gonna team tag on this, tag team.
yeah, and so our goal is to go through this as an introduction to the topics that we're going to talk about. And then there is a pretty detailed resource list that we did make available online as well. And so if you go to the UNESCO website and check that out, that's some really good stuff that we put together to supplement. And so the purpose, the goals of this is just to talk about managing resources, to make database decisions for good management practices. We're going to talk about how to get the most value out of the data that we have and the data that we collect and practices in doing that. And then talk a lot about accessibility, sharing, and reuse of data, which is really catching hold here. And so we'll start with principles of data management. And there's really like two overarching principles that have been gaining traction in the last couple of years. And so that's open data and fair data. Open data. So data kind of operates on this continuum where you have your most restricted access, your proprietary data only shared amongst the entities in the original agreement. And then you have sensitive data somewhere in between where you either have some personal identifying information or maybe locations or information about rare, threatened, endangered species. So that would be data that you wouldn't want to release as is to the public because it could have a negative effect on either the humans or the species involved. And then open data or open access that anybody can use and share. And there's been a really big push for open data in the last couple of years, as well as with FAIR. FAIR stands for findable, accessible, interoperable, and reusable. And so this kind of came together at the working group in 2016. And one of the important things to know about FAIR is that this applies, it's twofold. So it's not just to make it fair, findable, accessible, interoperable for humans, but we're also talking about machines and computers being able to find, access all this information. So findable is that your data and supplementary materials have sufficiently rich metadata that describe the information. And they also have a unique persistent identifier. So we're seeing a lot with digital object identifiers, DOI numbers recently. That is your persistent identifier. Accessible. And so that's where your data and metadata are understandable by both humans and machines. And so basically anybody with a computer and an internet connection can access the data if they have the authorization. And it's important to note that accessible data doesn't automatically imply that it's free or open access. You can also have data published with restricted access that follows FAIR principles. Interoperable. So it should be possible for humans or computers to interpret the data and combine it with other data sets. So you need to have proper documentation, use preferred file formats and clear structure so that other people can use this data. And reusable. And so again, with describing it with the metadata, you want to provide enough background information about how that data was collected, who collected the data, when it was collected, how it was processed, anything that was done with that data that would allow somebody, if they got that data set, they would understand and be able to go and take it and run with it. All that information is present. And so what do we mean by value in data? Oftentimes it takes a lot of time and resources to collect data. And so basically, if best practices are followed, the value of data is going to increase from the time of production through the time of use, and then even more with reuse. And especially as the impacts of the data start to be seen in policy and management decisions, does that value really increase? And so you want to be able to use data that you collected maybe 20 years ago. That took time, resources. You want to continue to use that throughout. And so techniques in data management, what are some ways that we can manage our data using best practices with storage and organization, documentation and description, and our long-term storage as well. So for local storage and organization, just on your computer, it's really important to have simple file naming conventions. You want to have descriptive file names that make it easy for you to find and sort through them. You can include information such as your project date, project name, content versions. There's some really good guidelines that we have in that supplemental resources manual on in-depth file naming convention recommendations. And that goes with file and folder organization or file management as well. You want a simple hierarchy. You want that organization and the file and folder names to work together, so you can also to make things more findable. Indexing, you can use your computer's resources. Your computer indexes all the files on it, and there's some ways that you can optimize the way that indexing works to improve your search functionality, and we can provide examples of that later. Keywords as well. You can keyword files on your own computer. These are another type of metadata, and they just improve the searchability and findability. If you type that into your File Explorer window, it'll find any file that you've keyworded with those keywords. We have information on how to do that as well. Documentation and description. And so it's really important to know what files you have. You can create a catalog or an index or list of files. And so if you have your project, if you have your data organized in a project folder, then you should have a list of every bit of every file that's in that folder associated with that project. And you want to maintain that, update that as you add new files to that, and include things like the extension, so .doc or .pdf, and where that file is located. Your readme.txt file would be in that project folder as well, and that's where you describe what the project was about, what the purpose of the project was, and what some of those files, in more detail, what is included in those files. And then the data management plan, this is something that more and more is required when you apply for grants and funding. And so it's really important. This documents the entire life cycle of your data, from the collection process all the way through to the archiving process. And so you want to have a plan set out from the beginning, and then you can follow that plan all the way through. And there's some really great resources in that supplemental guide with even some tools and prompts to write a data management plan for NSF grants or some other national funding agencies. Some more documentation is a data dictionary, which describes each field or attribute in your data table. That's something that could also be done in Excel. There's example data dictionaries in our supplementary resource guide. That's where you describe each column in your table, basically, what it means, what the units are, information that makes that easily understandable by somebody that's never seen your data before. And then metadata, we've sort of been talking about all along. That's your data about data. And so the readme.txt, the data dictionary, and the keywords, these are all things that are types of metadata. And so if you do that from the beginning and you start that out as you start your project and your collection process, it's much easier than having to go back and recreate that at the end. And that's going to be required for depositing your data in any sort of data repository. So in the supplemental resources guide, we have a list of data repositories or resources where you can type in what kind of data you have, and it'll help you find repositories to deposit that in. And so that a lot of times, more and more, journals are requiring for you to publish your data set as well as your journal article that you're trying to get published. And so this will give you some ideas of where to have that data published to meet those journal requirements. And so long-term storage, that is referring to those data repositories. We talked about the digital object identifier, which is assigned to journal articles, but also to data sets or other digital objects. And so if you actually type that DOI number in your web search bar from anything, it'll bring you right to that data set or that journal article. And so there's just easy ways to go right to that information that it's referencing. Repositories, they archive data for the long term and they make it publicly accessible. Non-proprietary formats, that's where it's open format. So if anybody downloads your data set, they can take it and open it. It's ready to go. It doesn't require some specific software that some people may or may not have. And in the supplementary resource list, there's a list of common non-proprietary formats to use. And then data standards. And so this includes like a consistent format or structure or vocabulary, which is also vocabulary and keywords are sort of synonymous. And so if you have these commonly used standards within your discipline, it makes that data combinable and usable more and more across the discipline. And so for an example of a use of data standards, we have the National Geologic Map of the United States. And so each state has its state survey who is responsible for the geologic mapping in that state. But it's much finer detail, much higher resolution, and then unit names, lithologic names can change across borders and boundaries. And so they came together and came up with a national structure and standard where they could take all the state data and combine it into a national map. And then you can go again to like international. And so this is one of the purposes and uses of standards, is combining and reusing the data. And then we're going to let Pat talk about tools.
Okay, so basically what Sarah is talking about and what kind of we mean is we're talking about the term data management. And that's like a really broad, and maybe it's a little bit ambiguous, but what we mean by data management basically is active data management, which means that you develop architectures, practices, and procedures to manage the data lifecycle. And what is the data lifecycle? Well, basically that's collecting it, storing it, and securing it, summarizing and aggregating the data in a format that makes it available for analysis. Of course, your data analytics in general, which let you explore and analyze and visualize your data. And from which you can extract insights, and also, that's where your guidance is going to come from for resource management decisions, and also for accessibility. So, slide. So, what kind of tools are out there for data management? Well, it kind of depends on what your data is, and also in terms of, are you doing it as an enterprise professionally versus are you doing it more sort of as a open source or community available data? So professional software this tends to be more high-end stuff and more specialized stuff. So as an example, if you have tabular data, Microsoft SQL Server might be what you want to use to help you manage your relational databases. If you're dealing with geospatial data, any data that has location associated with it, which I think is all data actually, ESRI products are what you would use to deal with that data. The actual digital asset management tools, and these are things that actually help you manage your data in a sense of storing it, securing it, making it available, basically all the things that Sarah has already summarized. And then of course we have our data analytics, And things like SigmaPlot or Origin Lab or MATLAB, these are all amongst the myriad of software out there that can be used to analyze and display your data. This stuff tends to be more high end and more proprietary. So if if you're not an organization or group that has the funding to use that kind of data or that kind of software or tools, there are certainly other tools that you could use that are affordable or even free. Sarah? Next. So your open source, I guess you can call it software, for your tabular data, you can use Microsoft Access or Excel. They're not, they don't do everything that the high-end stuff does, but it probably can cover just about all of your needs. If you can't, afford the ESRI products, there's QGIS or GrassGIS, which are more open source GIS. And you can do pretty much most of the same things as you could do with the ESRI products. For digital asset management, things like Google Drive, G Suite, Dropbox, those are all tools that you could use to help you manage your data. And then, of course, there's your data analysis and graphing. Excel is certainly, you can do things in Excel. You can do things in the geospatial data, but there's also other open access software, and R is a big example, which is very popular with many researchers because it's free, it's open source, and so there's lots of different applications associated with it. So, for any of these, probably your biggest expense is going to be the learning curve on how to use it. Next. So there's also specialty software, and when we're talking about karst and cave related stuff, as we all know, there's a lot of specialty software out there that a lot of our citizen scientists, and I'll talk about that in a minute, use to collect the data, to analyze it, and to show it. And I'm not going to go over each and every one of these different software applications, but we do have descriptions and links to them in the resource document. So you could go and explore all of them. They all have tutorials associated with them. And the stuff on the left, the walls, compass, caveware, Therian, and breakout, those are all specifically associated with cave data, with cave survey data. Visual Karst, this is actually another kind of form of GIS, and it will allow you to integrate your cave data in a 3D fashion with DEMs, with geologic information, with cross sections. I attended a workshop for that, and it does some pretty amazing things for helping you to visualize, what your resource is. Right now it's in beta version, and I think you can get it for free, but eventually it may end up being something that, is going to cost you something. Sarah? So I did mention citizen science and crowdsourcing, and pretty much there's a whole workshop on citizen science later this morning. But basically what citizen science, slide please.
Oh, sorry.
Citizen science is just allowing the public to participate in the scientific process. And in many ways that's in collecting data. Now, most citizen scientists don't have, say, expertise in water chemistry or, any other endeavor that you could use the general public to participate in. But what they can do is at least help establish a baseline for your data. You can't go anywhere unless you know what you have, unless you can see how it starts to react to different parameters. And so having a citizen science group that's collecting water quality data, that's kind of an example and a very common one. So there are watershed watch groups where they organize people to go out and collect samples, and they provide them with very basic tools so that you can look at water quality over time. I think one of the greatest examples of citizen science are cave mappers, which are cave explorers that are out there making maps of caves, and they're not getting paid to do it. I would say that's pretty citizen science. And many times cave maps are the basis or the beginning of the study of anything cave and karst related. There's some interpretation with citizen science. More so, I think I've seen it in cave data collection, because typically what your citizen scientists do is then they make a map. and that's interpreting your data. You can make new discoveries. Anytime you go out and collect data, try to analyze it and look at it, you're gonna have insights into things that you hadn't realized before. And of course, it's a way of developing technologies and applications. On the previous slide, all of the specialty software, most all of that was done gratis, just by somebody who wanted to do something with how can I use my data, and it's turned into technologies and applications that have turned out to be very useful for all of us. Next. So crowdsourcing, when we think of crowdsourcing, we usually think of, the Facebook page that's dedicated to collecting funding for a project or to pay a medical bill or for a charity. But, you can use that same term for the crowdsourcing of information. And three really good examples of the crowdsourcing of information is Wikipedia, which, we're all very familiar with Wikipedia. And that started out as just kind of a collective of people, having a means to put a bunch of facts together into an encyclopedia. And it has gotten more, I believe, credible over time as now that data is vetted. So that Wikipedia of maybe whatever, when it started, the way that it is now, I see it as being a much more reliable source of data before that time. iNaturalist is another example where, say as an example, bird watchers, okay, there's this coalition of bird watchers and then professional like scientists who study birds. So these guys go out, collect information, post locations, pictures, and your scientists can help identify what these things that they are looking at, and it gets to be a really good cooperative kind of thing. Another example would be OpenStreet, and this is not exactly, I would still call it crowdsourcing in the sense that people use that for navigation, but they can also edit that navigation map by putting in things like where the police today, or what the weather conditions are, or what accidents are, whatever. And so these are all things that involve the general public, which, I think that in terms of, this is data can be gleaned from all of that. Next. So the benefit of citizen science is that you start acquiring a baseline of data, for at least for the scientific type, professional type, and it basically it's just acquisition of baseline data, and you can expand your resource collection base, and also identification, and you can identify potential research questions, or maybe questions on things that maybe need to be monitored over time, like water quality or air quality. But not only does that benefit, the professionals, but it also benefits the public, because it can serve as public education and training. It makes people much more aware of natural type things, which maybe they hadn't thought about before. It gives them a stake in the outcome of this stuff. If people don't know something exists, they're not going to care about it. If they don't care about it, they're not going to, support it. And support comes in many forms, including money. So there's a lot of benefit to citizen science. Next.
Okay. So data management and resource protection. Here we're just going to talk about how managing data helps to increase your resource protection, and go in a little more detail there. And so I mentioned the kind of the life cycle of data, I think already today, but that's basically this cradle to grave mentality from the very inception of the idea and the collection of data all the way through to the end, the archiving and distribution of data for other people to access and reuse. That's this whole cycle, which continues with repeated use. And so each phase of that process is part of this data life cycle. And again, we mentioned the data management plan earlier. What that does is basically describe each step of how you're going to manage your data throughout each step of that life cycle process. So again, it's cyclical, but you describe out front, before you start your project, you have a plan for everything that you're going to do with that data, such as access, sharing, if you're going to share, so that you document everything that you've done throughout the process. One of the big things that we need to look out for in managing resource data is siloed data. And that's where you either have scientists, resource managers that are within maybe the same organization or agency, but they're operating under different disciplines and they have separate data sets, and there's not that communication there where you maybe have biologists and hydrologists, and some of their information can overlap. So if the biologists are looking for bat habitat and the hydrologists know where the caves are, but the biologists don't know where the caves are, there needs to be that communication. And so also different organizations or agencies can have separate data sets. And if there's no collaboration or communication across government, private, nonprofit agencies, you could have people repeating work, collecting the same data, producing the same data sets, where they could really benefit from working together. And so we need to watch out for siloed data. And then also try to integrate all our different data types. We have lots and lots of different data types. I think that, so that to integrate would be to consolidate your data from these disparate sources into a single data set. And I think that the first process in this integration can look like a lot of different things for a lot of different people. So there's not like one blanket answer of how do I integrate my data. And this is one of the most challenging parts of the process, I think. But I think that a data inventory is your first step. So at the beginning, we talked about cataloging, indexing, putting together a list of your files. That's sort of your inventory. So you've got to know what you have in order to be able to integrate it. And also along those lines is your legacy data. And so if you have data that's stored in old and obsolete formats, you kind of don't even know what's there. And so the first step would be to get that legacy data into modern formats so that it can be integrated with these other data types. And so I think that, that's what we mean here by integration. It's not a magical answer. One example is if you do have a data inventory. So for example, with the Kentucky Speleological Survey, we've got a tabular database or a relational database, which has cave entrance locations throughout the state. But then we also have all these related map documents or scientific reports, trip reports. So we have a tabular data set, and then we have documents and publications. So how do we integrate those together? So if we have our inventory of all of those documents and maps, that would probably be in another, like a tabular or Excel file. And so with that, you can then go and say, Cave X, map, yes, no. And so by including a column, just a yes, no answer, you at least know in one spot and looking at one table that, hey, this cave does have a map. I can then go and find more information. And so that's kind of what we mean by getting it in one spot. Other ways that you can do that, of course, are SRIs or any geospatial database. A lot of this information can also be integrated using a geographic information system. Data visualization.
Data visualization. Oh, one of my favorite topics. And so, if you look at a big table of numbers, that's not going to really tell you a lot. And so what we're talking about in data visualization is, well, what does our data tell us? Like, how can we get that from our data? Slide. So usually, I guess when I think of data visualization, I think of graphical representations of your data. A table is not, a list of numbers, a list of, assets or whatever. It's got its value, but it has limitations in terms of being able to look at trends or analyze your data or to see what outliers are. So graphical representations would be like charts and graphs and maps. And so with your data, it's the whole data management thing. It's not a static thing. It's a very dynamic and active thing. And so you want your data to be in such a format that you could use these different visualization methods to kind of take your data to the next step. Slide. So you're going to have different types of data, and all of it can be visualized in some way. I'm not going to go over each and every one of these, but what we have here in this table shows basically, say for instance, if we're talking about geospatial data, well, how can we visualize that? well, you could visualize it with, there's different kinds of maps or representations that allow you at a glance to visualize your data. If you have temporal data, or even time series data, things like scatter plots, timelines, line graphs, all these ways are different ways that you can use and see, you can see and use your data. And from there, you can gain insights, you can see patterns, and then you can base that, based on that, you can make your management decisions. Or, do we need to monitor something? Do we need further research? Do we need to collect more? That kind of thing. And so that's part of what I think of as data visualization. Next. So software limitations, or what are the limitations of your tools? And so you have to consider that your software is always evolving. Okay, what was good 5 years ago, maybe even last year, things are always evolving. And so, there's always that danger of your data set being in a format that's no longer being supported, or to be put out in formats that are not interchangeable. Early on, at least in the US, one of the earliest cave data graphing software didn't have a format that was interchangeable. It did have one format, but you couldn't just take their data and use it somewhere else. And I think that was part of the demise of that software. These days, things like WALS or Compass or any of the other software out there is interchangeable. You can port it to a different software if you want. So you have to take that into account. Institutional knowledge is important, whether, and that's sort of the human touch. There's the historical perspective on, well, what's this, what have we done with this data before? What kind of mistakes or issues have we had with them, and how can we learn from our mistakes? So don't discount institutional knowledge. That's always important. Data sensitivity is something to consider in your data. Is it something that should be widely available to everybody? What parts of it, are on a need-to-know basis? And there is no hard, fast rule for that, or one blanket statement for that. It really depends on the context. And you also have to be aware of data gaps. Why is there a gap in my data? Is it because my instrument quit collecting? Is there really a zero there? Or, you want to understand what the gaps are in your data, because sometimes they can also tell you something besides, the stuff that you do have. So you always want to take that into account. Do we have one more after this?
It's discussion. I was going to add a few things and then we can go to the discussion.
Okay.
An example for institutional knowledge, something that we've been debating and struggling with managing the data for the KSS, for example. So we're a volunteer nonprofit organization. We have some grants through Esri, and we have access to some of these professional higher end software types that we've mentioned earlier on in this talk. But our problem is, how sophisticated do we get? Because right now we have the personnel, the volunteers, who can get fairly sophisticated with managing this data. But the problem is, people come and go, volunteers come and go. And so what knowledge will the next upcoming people have? And will they be able to use this more sophisticated management system? If not, and if we don't have the proper metadata and all these other things in place, then the data can be lost. And that's something that other organizations have had happen and have struggled with. And so that's sort of also something to keep in mind with institutional knowledge. And then with data sensitivity, I don't think that I mentioned it earlier, but also in that resource guide, you can anonymize your data, and there are tools and guides out there to help you do that. And so if there are bits of sensitive information in your data set, but you still want to publish that data, then there are things out there that you can do to allow you to hide that data that's sensitive, but still publish that data set. And the USGS is leaps and bounds, I think, ahead of the game. And they have a lot of resources that we list, and that resource guide came from the USGS, and they've really done a good job with managing their data.
And I think somebody just put up the link to our, I think Autumn did that, right? Did you do that, Autumn? Thank you. Put the link to this data resource thing that we've been talking about. And basically what we did was anything that we mentioned in this talk, we put the link to it and maybe a little bit of a description of what it was, so you didn't just have this list of links that after time becomes meaningless. So really the whole big purpose of this talk was to kind of instigate some discussion on people's experience with data management, or maybe some questions about data management. We are not, by any stretch of the imagination, the experts. But, so that was part of this, is to gain some, I guess we can call it crowdsourcing of information, in the sense that, what are other people's experiences, or what kind of, challenges have others had. So we kind of want to open it up for discussion, and we welcome some input from you all. Don't be shy. If you don't want to talk and you just want to type in a question, that's fine too.
Yeah, when we went over this yesterday, and it took Pat and I over an hour to go through it. And we were like, we really need to condense it down to allow people to tell us what they want to hear about. But we can expound on any of this a lot more than we have. So I know it's dense, and we kind of ran through it. But we want to hear what you want to know about.
Hi, this is Kurt.
Hi, Kurt.
Hi, guys. Really enjoyed your talk. One thing I feel like was missing, however, and perhaps deliberately, is how we are collecting the data in the field. One thing, it's the thing that still sort of grates on me personally in my work, in that we're still using, I have yet to find a good rugged electronic device on which I can collect my data. And obviously having the field data sheets pre-programmed and being able to fill them in the field reduces transcription error back at the office. Obviously, that doesn't eliminate errors in the field entirely, but it sure reduces them when you're getting the data into the database. So that was. So what I'm looking for is maybe suggestions, or what. Obviously, some people still use pencil and paper. That's sort of the old reliable. But others I've seen over the years use electronic devices, and obviously, as cavers, we have a series of challenges that people on the surface do not have.
Well, one thing you are correct is that we didn't deal with that, because that is practically its own topic. But I know that there is another workshop this morning that they do talk about different methods for data collection. I believe that's Jason Polk's, and I don't know how he titled it, but I think part of their discussion is going to be things like, what's the best way to collect your data, whether you're doing time series data or temporal data. As far as what you're saying, Kurt, I totally agree with you. There's not some consensus of, well, what's the best way to collect our data. Now, I think KSS and Sarah could probably speak to this. Didn't you guys have some setup in some way where people were able to collect on their phones, like cave location data, descriptions, pictures, whatever, that they could collect for the KSS database, and then you could actually send it to them from the field? I think you guys were doing that at one time. How did that work out?
Yeah, so Ben Tobin and I are working kind of as part of the KSS and then as part of KGS as well, with the Kentucky Office of State Nature Preserves, and helping them do biological inventory in cave. And so what they're working on is just a Esri Survey 123 app, which again is sort of your citizen science, getting cavers involved in collecting data on invertebrates in caves. And so that would be a cell phone device, and that's, I guess, is rugged or not rugged depending on what case you use or whatever. I know a lot of cavers that have broken their phones in caves, and so I don't think it really necessarily answers gives an answer to Kurt's question, but it's something that we are doing. And with that, something where you can collect the data while in the cave, but obviously you couldn't transmit that at that time anyways. So you can transmit that data once you get back home or into cell service. And so I guess you could like pull your phone out, use it to collect the data and put it away between like moving through the cave. But I mean, I agree, it's not a great solution. And it's more geared towards the citizen science.
And I guess as
Well,
far as, go ahead.
yeah, go ahead.
No, this is for you. You go ahead.
Oh, I was going to say that you mentioned Survey 123, and that's that seems to be gaining popularity in the inventory and monitoring division as a program to use on whatever your device is in the field.
Mm-hmm.
And Clint, everybody's looking at the chat, but Clint is saying that Florida Geological Survey is using tablets and laptops with ArcGIS Collector app. Of course, he says we don't have many dry caves to deal with, but I think you do have some dry caves. But yeah, definitely, you know, underwater, like, what do you do with underwater stuff? One thing I would like to say in terms of your data collection, like things that you could collect data with, in terms of cave survey data, you know, we all know, those of us who map caves, that the Disto-X is kind of a cool, wonderful device because you can collect everything electronically. You can send it via Bluetooth to a tablet, and you can actually, you know, draw it as you're going in the cave. Now, the drawing part of it, I think the technology, it still needs to evolve to make it practical. But one of the reasons I bring that up, aside from, you know, it's a cool thing to be able to do, is that the one of the devices that's kind of critical for the Disto-X is no longer being made. So that would be the Leica Disto laser rangefinder. That there's a special piece of hardware that you have to put into this device that turns it into the Disto-X. Well, they're not making that anymore. So now we have an issue with, well, you know, what do we do next? And so I don't have any doubt that someone can come up with a substitute, but that's kind of like a real life, you know, situation. So. And
Kurt, another thing that we tossed around with the KSNPC on kind of related to Survey 123 and cavers collecting biological data in cave is iNaturalist. And I think that they actually like tested that a little bit, but so it's based on algorithms and it learns from prior experience, right? So the problem is that there's not a whole bunch of people out there using iNaturalist to identify cave bugs, so that the algorithms are really poor at this point, and it can't like correctly identify what it is. But the more input data that you get in there to like train that and train the algorithms, that you could use iNaturalist for cave critters just like it's used for surface critters at some stage, maybe.
It looks like Mario says he would like to make a comment to the discussion, and please do. You might want to unmute yourself.
Yes, thank you very much. And first of all, Sarah and Pat, thank you very much for this workshop. It was very interesting. I like to add another issue to the discussion because I think that when building a database, especially nowadays when there is possibly a huge amount of data to being put together, a problem can be the reliability of the data. I'm thinking, for instance, to cave maps. For a specific cave, I can have a map that was produced 50 years ago, then another 20 years ago, and another this year. And so a question may arise, which one is the best? Many people would respond probably the most recent one, but this is also a matter of the tools, the devices that have been used when producing the map. And also the expertise of the people. If you put very good device in the hand of people who are not familiar with them, the result is awful. I mean, it's not reliable at all. And so this is a very important part of building a database to me, that is, of course, in the end of the data manager, he or she should be able to assess in some way the reliability of each set of data. And this can be done if you know the device which were used for mapping the cave. But if you have no information, this might be very difficult. So I would like to know your opinion about this.
I'll speak to that. And one of the things, and I'm gonna, well, being that I am a cave mapper and a cave cartographer, and in our cartographic salon for the National Speleological Society, one of the requirements to put on your map is to say something about the instrumentation that was used to collect the data to make the map, and also what standards were used, because standards vary by region. It varies by, when, 20 years ago, the standards are different than they are today. And so at least, when we looked at a whole bunch of maps when we judged maps in our map competition this year, and most of them had, what instruments were used. They might have used the BCRA cave standard, or, so that information it hasn't always been included on the maps. And so Mario, you're absolutely right about that. And I think we need to encourage cartographers to do that, because when you're out surveying, you have a standard that you're held to when you're collecting your data, and it's different for different groups. So to understand and to know what standard a group mapped is important. The BCRA, I thought, came up with a really good idea. I think they have a 5 or 6 grade standard that explains, if this is what you did, did you make a sketch? That's got a different standard than if you did it with, full, say if you did it with LiDAR or something like that. So you're absolutely right about that. And I think that's a really important consideration when you're talking about especially these kinds of databases. So definitely thank you for bringing that up, Mario.
I think, and on top of that, there's a big discussion right now about like data certainty and data veracity, and how to apply some index or number to the uncertainty of the data and integrate that within the database. And so I think that there was just a meeting 2 weeks ago with ESIP, which is a resource listed on your resource guide, but that's Earth Science Information Partners, and they had a big discussion about how to handle this problem. And like basically the end result of the discussion was like nobody knows, and we're aware of the problem, but there's not like a really good answer right now as to how to tackle it. And I know that like I think it's the Geological survey in Alberta. It's one of the Canadian geological surveys. They did an entire 3D model, subsurface model for their entire province. And they applied uncertainty values to the different parameters within their data set. And so this is some sort of like numerical representation of how certain or uncertain you are of that piece of information. And so I think like with smaller data sets, maybe like the data manager, so for caves, for cave maps and cave survey, maybe the data manager knows the people that are turning that information in well enough to say like, oh, I trust this person's information and I know that they collect good data and are very accurate. Whereas I know that these people are a little more sloppy or something, but that would require a small group of people and a data manager that was familiar with those circumstances. But then you get, like you're saying, like 50 years out or more, and it's how do you deal with that? One of the things that we do with the KSS and the Survey 123, a lot of our cave locations are wrong because they were plotted on topographic maps by hand 70 years ago. And so even if you send people out in the field with this Survey 123, even if we already have that cave in our database and somebody reports it a second time or a third time or a fourth time, every time that it's reported, it allows us to double check the information that we do have and then correct it from there using like the more accurate technology of today. And so that would be kind of like some input I have to the discussion. But again, like there's not really an answer. That's a good one that I know.
I think one possible answer might be standards, the data collection standards, because,
Yes.
going to have their own idea about, how to collect data. I've done a lot of survey in the Yucatan as of recently, and there was a caver down there who he didn't consider himself to be a caver, but he was very much interested in exploring caves. And what he did was he actually mapped a whole bunch of caves and he made up his own standard. Because he didn't know about NSS, he didn't know about cavers, he didn't know about anything, but he actually came up with his own standard. Now it wasn't, so when organized, project caving made it down there and we went down there with a specific standard, I mean, you could see very much the difference in the data that we collected. And so, by everybody doing it the same way, I think that really helps to establish a credibility of, how accurate is my data, and also to say, well, we mapped it by these standards. Different survey groups in the US have different standards. Do we do backsites? Do we always do a profile? So there's not, and of course in the US we're notorious for not wanting to have standards. But I think standards would really help in all ways, not just in how you collect your data, but how you represent it, and how you display it, how you report it, whatever. Mm-hmm. Let's see. Erin.
Well, Katie, actually, I just couldn't change my name.
You're right. You even said that in the beginning, and I was like,
that's okay.
Hey.
One comment I wanted to make, I work for the Pennsylvania Geological Survey. One thing I've seen working for the Pennsylvania Survey is it's important when you make a database to make it so you can adapt it for when you so you can add new data when you get new data or change data types, because a couple years ago we updated a database we had, which the old database was not updatable, and we couldn't add the new forms of data that we now get.
Do you mean that the format, or that the format was not updatable, or the means that you had to put the data into your data set was not?
This is an oil and gas well database, and now we've got lots of horizontal wells in Pennsylvania. The old database did not have any places we could put information for horizontal wells in the database.
Adding new fields.
Yeah, adding new fields or.
Yeah, I think that the database design is really difficult. If you're starting out and building it, you need to think of everything that you can dream of, like in your wildest dreams. What would be the most, impressive, ideal database to answer the questions that I want to answer when you design it. And even if you don't put those in from the get-go, have this sort of grand plan in mind and make sure that you've designed it where it could adapt with different things in the future. I mean, you're still going to run into problems like that. Yeah. But if you have sort of a data management plan to go off of at that beginning process as well, those two can kind of complement each other. But it's hard. So. Anybody else? Well, we had some other points of discussion we thought we could throw up there in case.
In case everybody quit talking, we're not.
So here we are.
And so here were some questions that we thought about, maybe. Let's see. I think maybe proprietary, sensitive, and open, maybe we've actually discussed some of this. Is there anything on this list that anybody has any comments on or wants to see further discussion on?
And I think some of these have come up in the discussion already too. So the data structure and design, Katie just mentioned, and then the uncertainty that Mario mentioned. one of the things that I've been struggling with and haven't found a great answer for is that first one. So how to locally georeference resources in a cave. And so, you know, your cave is a resource in and of itself. And so you have sort of a database of the cave locations. But then you also have resources within that resource. So your archaeological, biological, hydrological, anything that you would inventory in a cave. Assigning locations to some of that isn't really well defined, nor is sort of integrating that within GIS. And so, you know, when you do an inventory and you're looking at what species are near this station, or sometimes you do, you know, halfway between one station and the next station, but there's not a really defined location where you found that resource. And in some cases, the map can help pinpoint that location if it is something like water or formation that's noted on the map. But in other cases, especially like the biological, where that stuff moves around.
It matters to me a lot.
How do
So
you,
it's just a way to do that.
and I don't know if anybody has any answer, but how do you
For
do
looking at
that?
mineralogy,
Well, I can,
I always try to reference survey stations, location relative to survey stations in the cave.
Of course, it's like the survey stations are different lengths apart. And so in an inventory, in a mineral inventory that I participated in LIFECYCLE Cave, as a matter of fact, we were trying to figure out how can we geo-reference the various different minerals that we see, mineral occurrences. And Sarah briefly mentioned this. What we came up with, and I can't say that this is the most effective way, but it was at least something to kind of, you know, give us some ideas. And basically what you did was you figured out what was halfway between your station and the next station, and halfway between your station and the previous station. And that's not going to be the same because the station lengths are all different. But that was kind of how, you know, we decided.
Yeah, $12. Siemens
Another thing that you could do is just
fundamental
take a
3D
survey shot.
modeling course. Much content is here.
Rachel?
yeah, so what I do, I have several long-term erosion monitoring stations, and so each of them is
Stephanie and I were just talking about
surveyed to tie it
Roots and
into
Coursera
at
and
least
Udemy
two
and these kinds of things. Right now, I'm
stations
looking at
on
an
the
NX
cave
course on
survey.
Udemy that's $12.
And so that way it's a more robust way to geolocate it in the cave, because if you just like give an approximate place, we know that's just approximate. But if you just tie it into one station, then
No,
you can,
it's
you know, you
actually,
kind of have like this
40
flopping dangling thing. But if you tie it into two, you have a solid triangle, and you
So
can,
they're selling it for
you know,
$11.99
get that tied
US.
into the cave map, which is
Nope, that's it,
hopefully
forever.
in
Udemy-
most
Udemy
cases,
courses are
you know,
forever.
you can
So
georeference
somebody
back to
pays
an entrance at
$12
least,
and they have
if
access to
not
this content.
Nice.
closer in.
And then,
Possibly.
Kurt, I know that you've done population studies.
Interrupt for a second. Someone's talking in the background, and it's like almost talking over us. So if someone's back there talking, could you mute so that we could? There you go. Okay, now, sorry.
I know that Kurt's done cave cricket population studies, and so if you're looking at like how organisms move seasonally, like closer or farther from the cave entrance or something, Kurt, do you have something that you could offer?
Yeah, so I mean, it's almost like a cave survey. We use a baseline of fixed length, depending on the cave entrance, and have instructions as to how to lay it out. Not exactly, but very close each time, so it's reproducible. And then we just shoot distances off of that baseline. And you know, with respect to clusters of cave crickets and stuff, how they so we can reference the size of the cluster and how it contracts and expands over time, and if they're moving with reference to the baseline. And then So we have that distance, and then we note whether it's on the wall or the ceiling or what have you. And those are typically the choices, wall or ceiling. With more mobile organisms, you know, obviously that's going to be a tougher thing because they're moving around. Obviously, cave crickets move about too, but most of the time they just sort of hang out in clusters of various sizes. The other thing that we do is along that route we'll have data loggers, such as temperature relative humidity loggers, or in the case of cave aquatic biota, we have places where we put in pressure transducers and temperature data loggers. And in those cases, we take images of, so we have the location of where the data loggers hanging or where it's been affixed in the cave, and then we then we take pictures of a landmark nearby from where we shoot a distance to the very familiar landmark. We take a picture of that and add that into the database and shoot a distance to the instrumentation from there. And you know, particularly for a cave that you're very familiar with, which, you know, we all have caves that we're extremely familiar with and know the cave, and it's a good way to go about it. We try to make it as reproducible as possible for people who might not be familiar with the cave, you know, by having those images of where the landmark is, and also where, the instrument in situ. So those are the way we handle those things for the population monitoring. The other thing I wanted to mention was, you know, obviously having documentation about all these procedures is extremely important. And whether it's a data quality standards document or whether it's a step-by-step protocol as to how you're collecting the data, and you know, nothing is more valuable than having that step-by-step cookbook. If you want, obviously data changes over time, but if you want continuity for some time period, then having that kind of cookbook is invaluable. Obviously, there's the training is also very important too. I mean, you can have a great step-by-step process, but if the person hasn't been trained how to do it, that's a very important part of it.
That's a good point. Does anybody else have anything that they wanted to focus on or questions on some of the stuff that we blew through quickly in the talk?
Well, I have something to throw out there, or a question. So how do people deal with like their LiDAR data or LiDAR data in general? Or maybe nobody does, or whatever. Katie, are you making, I would be happy to talk more about data visualization. Well, LiDAR is data that helps you visualize the cave, but what?
PK, I use LiDAR data, but I don't really understand your question. Can you be more specific?
Well, okay, so what is the most useful thing about LiDAR data, like how you're using it? Because I think that, you know, we're all wowed by the data itself, or by, not the data, we're wowed by the product of the data. But, you know, what are the sorts of things that you could actually do with this, like more than just make a, you know, cave map or a 3D model? Like, what are you doing with it? You're doing more than just...
Well, I use it to build 3D models, and then I use those 3D models as as boundary conditions for numerical modeling.
So are you actually able to measure features off of it so that you could, say, quantify something in particular, or?
Yeah, yeah. I've also, so I've pulled the, you can transform a point cloud into a digital elevation model, and then you could pull, and then I use QGIS, but you know, whatever geographical information system of your preference. And then you can do all kinds of different analyses on the LiDAR collected data in that framework, like, you know, pull profiles off of it and things like that.
I've also known people who've used LiDAR to look at changes over time.
Mm-hmm.
Like, you know, so landslide growing.
Right, so you can put it into Cloud Compare and do.
Provided that you have the old old data to compare with new data.
Right, and then, you know, and then it has to be within, you know, you have some kind of error tolerance for the thing, and you have to really have some places that you know did not change to pin it to.
Okay.
So that is, I find that to be a challenging aspect of working with three-dimensional surfaces like that.
Well, I find with our cave data is challenging to visualize with just regular cave data because of, well, standards is part of it, but the way that the process that we use, like where we set our stations and what we measure, that really affects, you know, what your quote product is going to look like, which is why, you know, LiDAR and a cave map don't necessarily look the same, because of, you know, how we collect the data. You know, what does your surveyors think are important versus what is really important. And I think that that's kind of a challenge too. If you ever tried to use data, just straight out cave data to do, you know, to make a model of the cave, you really have to do a lot to that data to make it useful.
So one thing we have done is take that LiDAR data, and this is, you know, being able to use the cave survey data and the LiDAR data in concert, which, you know, speaks back to, what is it, the interoperability part of data, where we take that LiDAR data, put it into the GIS, extract contours of the cave floor, and then use that as a layer in Illustrator along with drawing the cave map to better and more precisely represent the cave morphology.
Making
That's cool.
Like a underground topo map, basically.
Yeah.
Yeah, you definitely can't do that with straight out cave data. Not
right.
Like, you can if you specifically are aiming to do that, but it's not easy, and I think that, you know,
that would be tedious. Yes.
Yes, I think I've helped or tried to help Kurt help with some of his work that he's doing in the field, and trying to adapt like the cave data to get what Kurt wants out of it. That was not always an easy thing to do either. I don't know if he's still here, but anyway.
I am.
Well, was it ever useful, Kurt?
Oh yes, yes. Particularly, and we still have some mapping to do.
Well, just tell me when, man. You just never talked to me.
Sure. No, I know. But mapping, that what I was talking about earlier, you know, having these baselines off which we locate the cave cricket clusters, mapping those in the cave, you know, so they're reproducible, as closely reproducible as possible each time, was super valuable and very helpful. And particularly, the other thing that was helpful was, you know, doing the smaller scale maps because our longest baseline is about 40 meters into any one cave in which we're monitoring the cave cricket populations. So doing those smaller scale maps, so I'll be able to, plot those cluster sizes over time and have like I've always envisioned having, the clouds growing and shrinking and moving over time to show where they're going, or if they're going anywhere, or if they're staying in the same places, or what have you.
Okay. It's good to know that cave data has multiple uses other than just, what we use it for. Let's see.
So,
Rachel, you said something about after georeferencing. I think we should touch on version control, best practices for collaborating. Since we've got, 15 minutes left?
yeah, that's kind of a big topic for 15 minutes.
Well, make it short. It's a good one.
It is. It's really important, especially like a lot of the projects that we've been talking about throughout this workshop are very collaborative projects with a high volunteer turnover throughout time. And so being able to have a clear chain of what changed when and how to integrate changes into the whole data set is really important so that, so you know what data is valid. So you, for example, can accurately calculate the length of a cave, and so that you don't lose data by someone saying, oh, here's the new map, and replace the old map.
So I've been chatting with Kurt, who has an example of a data quality standards document that he was going to pull up for us. If he's able to share his screen, I'm not sure. But Kurt, whenever you're ready, you're welcome to go ahead and give that a try, and then we can figure out the screen sharing if we need to.
Okay, give me a sec.
Cool.
If Autumn is still here, there you go. Well, that's what do we got? That's ours.
This is some extra how-tos that I had as well. While Kurt works on that, I mentioned that like you can keyword files on your computer, and so I was just going to show you like how to do that. And so for something like Microsoft Word, PowerPoint, Excel, whatever, all you do is right-click on that file and bring up the document properties. And in that document properties window, there's the options to add tags, which are keywords. And so and you can see like it even gave me a little drop down menu to choose from when I started typing. And so you can keyword your files, and anytime you search one of those keywords in your file explorer, it'll pull those up as well. You can do that. It's a little different in Adobe. With the Adobe documents, you actually have to do it in the Adobe program. It won't let you do it in the document properties if you just right click that. So, but open the document properties for that document in Adobe, and then you can do your keywords. There's even an option there for additional metadata. So that's a little how-to and some little tips and tricks there. And then maybe, I see chat. Oh, cool. And then indexing files, you can also change your file indexing options on your computer to make things more findable, searchable, discoverable. And so with that, if you type in that search bar next to your Windows or Start icon, you can type in indexing options, and it'll bring this dialog box up. And in that, you can change where it searches when you search in File Explorer. These are like the default locations, but you can modify those locations yourself and add to that list. In the advanced options, there, for example, you can index the properties only, or you can index the properties and the contents of that file. So for Word doc, I definitely want it to, when it searches, I want it to search the contents of that document as well, not just the file name. And so you can, for each document type that you can have, you can choose how you want it to search that or index that properties or properties and contents. And then you can also, let's see, what did I have over here? You can also tell it if you want it to index your encrypted files or to treat similar words with diacritics as different words. So, and that's like if you have a little like accent mark or like cafe with an accent mark over the E, it'll search those differently. It'll recognize the differences there. And so those were just some how-tos we threw in as well. So.
Was Kurt able to or have something to share?
Yeah, I'm here.
Okay.
Sweet, are you ready?
Yeah, I'm ready.
All right.
I've been enjoying your indexing tips. Those are really great. I was too interested in watching those.
Sorry. All right.
Did we include that in our resource document? We talked about it.
So I was gonna put together a separate like how-to page for each of these. And so I think like you'll still be able to access the links for each workshop after, you know, and Autumn can answer to this. Like, even though the workshop and UNESCO Karst Conference is done, I think you should still be able to go to those links and look for the resources.
Yes, that's correct. So you'll want to check on the supplemental materials page, which is linked into the registration portal.
Yeah, we talked about doing this, and so now we need to do it.
Yeah, so I'll do that, and I think we do have an email list for the participants, and so I can also like say, hey, those are up now, find your how-tos on the resource list. So sweet.
Okay. So Kurt,
Kurt, yeah, give it a shot. Awesome.
Okay, can you see this?
Yeah.
Oh, yes, I remember this.
Okay. So this is just the cover page. This is a standard title, data quality standards for monitoring, blah, 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 whatever it is you're monitoring. Authors, table of contents, intro, protocol overview, you know, what you're trying to accomplish. Protocol activities and modules. So you've got your activity, how you're getting to where you're going, what kinds of field observations you're making, what you're writing down, and then the data you're collecting from your instrumentation in the field, and anything you might be gathering externally. So for instance, in the Cave Cricket protocol, I'm gathering weather data from the surface that have been vetted by, cleaned and vetted by experts such as temperature, relative humidity, and precipitation on the surface. And then what you're doing, how you're deriving those data is important as well. The data that you collect in the field, what is it you're gathering and how you're processing it? And then your quality control process. So what we do is, very quickly, we locate clusters of roosting cave crickets. We take pictures of them. We use typically several pictures of one cluster. What you could end up with is, literally, we end up with hundreds of pictures of cave crickets. So how do you determine what picture goes with what part of the baseline and where it's located and so forth? So at the end of the series of images, we have a storyboard that lists, okay, so this is from this date, this is from this cave, and where we are on the baseline. So we're at 4.1 meters, and this is cluster number 3. So those little things like that are important for your data. And then expanding further on exactly what your processes are in these tables. And then what are the objectives? What are your data quality objectives? So what kind of accuracy do we want from our instruments? And what is the instrument's capacity? Can it collect data within your standards?
Wow.
Let's see.
So was this an evolving document, Kurt, or is this something that you did before you collected anything, or
This is no. This is still a draft document, and for at least for the cave cricket monitoring protocol, and it is currently evolving. I'm working with a quantitative ecologist in the southeast region to further develop my data quality standards. As you know, the idea being. This sort of, in my mind, goes back to citizen science, which is fantastic. I mean, those people who help you out in the field are beyond useful. However, you can't just turn them loose. There's got to be some standards to your data, and this document lays those out, and particularly who is collecting the data. So are they a field subject matter expert, and what is the reference that they're using to collect those data and identify them? And so what I was going to see about is if this is a very specific document, but this is from a template developed by the Inventory and Monitoring Division, and I mean, if people are interested and I can share the template, I'd be happy to do that.
I think that would be a great idea because it's a really good example. I think it could be, modified to meet different purposes. I also noticed at the very end that you had a reference list, which is also great. Yeah. So if you wouldn't mind, I think Rachel was asking if this was available. So she gives me a thumbs up.
It may very well be. So that's the other thing I was going to mention is these data, the data with okay, two things I was going to mention is if these documents have developed and you find one like that and they fit your needs, don't reinvent the wheel. By all means, modify it, but use this stuff that's been developed previously. It'll save you a lot of work and a lot of heartache. Like Sarah was saying earlier about thinking about your database and the wildest things that you could possibly put in there. Odds are there's something close that has been developed out there, and you could modify it to suit your needs. The other thing is, in the past decade or so, the Park Service has been making their data more transparent. And so, to answer Rachel's question, I would be surprised if this template to this document is not posted on IRMA, which is the Integrated Resource Management application that is accessible to the tax-paying public. So I will look up and see if that template is up there, and then I can share that link with you. So thanks for the question, Rachel. That reminded me that, and to that end, there are many reports and data sets and stuff like that also available in the data store in IRMA. That's the acronym, Integrated Resource Management Application.
Great, thank you.
That's awesome. There's a bunch of yep.
I was just going to say, I'll look for that right now.
Yeah, this is all great, Kurt.
I mentioned the USGS earlier. They also have a lot of published data sets out there and available for people to use and reuse that has great metadata on it. And so if you're looking for data to use, that's another good source. And then one other thing that I thought of when Kurt mentioned like who is collecting the data, I thought that was I thought of an example that I ran into where that was an important piece of information, and it ties back to Mario's point and question about data uncertainty and data quality, and how to gauge that. So I was working with transcribing well lithology information from completed well reports, and I had a student employee who was doing this for me. And he kept coming across shell in the lithologic log, SHELL. and he logged that in my data input form as limestone, because shells make up limestone, right? So that makes sense to some degree, but this was in far eastern Kentucky, and there's really not a lot of limestone in far eastern Kentucky. And so what we figured out was that there was a specific driller who was drilling these wells that spelled shale, S-H-A-L-E, as shell, exactly how it sounded to him. And so then we had to go back and change all these entries to shale, S-H-A-L-E. So there's a great example of why who collect the data matters. And
Okay, great. So I think it's, is it 9:30, Autumn? Are we like done? Well, we're never done, because you know when you talk about data, you're never done.
It is 9:30.
It is 9:30, and we really appreciate everybody's participation. I think that some really useful stuff came up, and I hope that everybody, you know, got something out of this. And we will go ahead and put up that material after we're done here. After we go to another workshop, right? We have to participate.
yeah, I'll work on it this evening. It's been a busy week.
Can I quickly share my screen again just to show people what IRMA looks like?
Absolutely.
Yeah, of course, please.
Thank you.
We should have recruited you too to be in this workshop as a presenter. Ah.
So here is the data store.
Cool.
IRMA, this is, you can access this. You can see the URL there. And this is, all I did was look up data quality standards. Now I haven't filtered through it yet, but look at all the examples I got of data qualities, just looking up data quality standards. But I will definitely look through that and find either a good published example. As I said, mine is still draft, or maybe they've posted the template somewhere.
Okay, great.
Awesome.
Well, thanks, Kurt.
Cool.
You're welcome.
Thank you, everybody. I think this is fun. I'll nerd out about data anytime. So
Thank you.
sweet. All right, everybody. Well, we'll see you maybe this